Hello, this is Robert Davies with the Utah Climate Center. In this episode of Utah Climate Notes, we're continuing our look at why climates change. Now, last time we looked at regional climate cycles. This time we're looking at a very different kind of change, permanent shifts in climate at a global scale. To frame this conversation, we've been looking at the concept of energy flow. And we've already discussed how energy flow within the Earth system gives rise to regional climate cycles and short-term fluctuations, variability. This time, we're going to look at a very different physical mechanism for change, the overall balance of energy flowing into and out of the Earth system, producing long-term shifts in the planetary climate. We know from many lines of geologic evidence, fossil deposits, ancient shorelines, ice and sediment cores to name just a few, that in addition to regional climate changes that last a few years or maybe a few decades, the entire planet can and does undergo wholesale long-term climatic shifts. The ice ages are a specific example of such shifts that we'll examine in an upcoming video. But first, it's worth having a closer look at how imbalances in this flow of energy arise, causing the planet to warm and cool. And we'll start from the beginning. Imagine an ice ball of a planet in the cold vacuum of space. Now ignite a star about 93 million miles away and name it the Sun. The energy coming to the planet from the Sun comes entirely as light. And that's it. That's all the energy entering the system. And the ice ball reflects some of this light, most of it actually, but it absorbs some as well. And as it does, it begins to warm. And as it warms, it emits light of its own. And this light carries energy away from the planet. And the warmer it gets, the more energy it emits. Eventually, we reach a balance, where the energy coming in is equal to the energy leaving, and the average temperature reaches an equilibrium, neither warming nor cooling. But things can change to upset this balance. The Sun may change the amount of energy it's emitting. The planet's orbit may shift. Things may happen on the planet itself, such as the emergence of life, that alter the composition of the atmosphere, all of which will alter the flow of energy. And when the flow changes, so does the temperature. If events conspire such that more energy leaves the planet than enters, for example, the planet will cool. And as it cools, the planet itself emits less energy. It dims until energy flow is once again balanced and the temperature stable. Conversely, if less energy leaves than enters, the planet will warm. More energy will be emitted until balance is once again achieved. Now, say what you want, but it should be clear at this point, or at least plausible, that relative to the complexity of energy flow within the Earth system, the intricate ocean currents and atmospheric circulation, the physics of energy balance is much, much simpler. So, if the planetary temperature is changing, and we want to understand why, there are really only a few suspects. Energy coming in is from the Sun, and energy is leaving either as reflected sunlight or as the light the Earth itself emits, which we'll call Earth glow. If Earth's temperature is changing, it's because one of these three things is changing. It's that simple. So now a bit more detail regarding the planetary climate shift currently underway. And since the planet is warming, it would appear the incoming flow has become larger than the outgoing flow. And one way this could happen is if the incoming energy flow has increased. Well, since this flow is entirely from the Sun, it's straightforward to explore this possibility. We can measure incoming solar energy quite accurately, and here's what we see. A rock-steady, constant flow of energy over the past 40 years as measured by satellites, with just a few hundredths of a percent up and down from the 11-year sunspot cycle. So, while the temperature has been going up and up, the average incoming energy has stayed rock solid. Well, this leaves only one possibility. Apparently, it's the outgoing energy that's changing, specifically getting smaller. Again, the outgoing energy is the sunlight that has been reflected plus Earth glow. Sunlight is reflected back into space by bright surfaces, such as the Greenland ice sheet shown here, and by clouds and small particles in the atmosphere called aerosols. Well, it turns out that the total reflected energy is decreasing a bit. But this change is a response to the warming temperatures, not the underlying cause. Instead, it's a change in the energy leaving through Earth glow that's driving the change in temperature. So what exactly then is Earth glow? Well, it turns out every object in the universe, including Earth, emits light, the color of which depends on its temperature. So take the coil of an electric stove. We've all seen them glow orange as they heat up. But in fact, that coil was already glowing when it was cool at room temperature. It's just that our eyes can't see the color of the cooler glow, which is infrared. Well, likewise, the Earth, because of its temperature, is emitting infrared light, and that light carries energy away into space. So why is Earth suddenly emitting less light? Well, actually it's not. It's just that less of that light energy is able to escape into space, and the reason is the buildup of greenhouse gases in the atmosphere. And because of their molecular structures, greenhouse gases like carbon dioxide, methane, even water vapor, absorb energy that is leaving the Earth in the form of light, and convert that energy into thermal energy, warmth. This is the so-called greenhouse effect. And further, not all greenhouse gases are created equal. And carbon dioxide, it turns out, is one of the prime control knobs on the climate dashboard. We know carbon dioxide levels are rising because we can measure them. As a result of humanity's burning of fossil fuels, the atmospheric CO2 concentration has risen nearly 50% in the past century, and most of this rise in the past 50 years, shown here. As a result, energy that used to be escaping the Earth's system is now being trapped instead. And as the outflow of energy decreases, while the energy inflow stays the same, the planet warms. So exactly how far out of balance is this energy flow? As it turns out, not a lot, or so it would seem. Only about 2 units out of a total flow of about 1,400 units. And the units are watts per square meter for anyone interested. Well, to put this into context, that's about 1 Christmas tree light's worth of energy for every square meter of the planet. Energy that used to be leaving the planet, but is now trapped instead. Now, that may not seem like much, but it adds up. For scale, that's about 4 atomic bombs worth of extra energy every second, or about 1 million bombs worth of energy every few days, day after day, year after year. So if you're imagining 1 million atomic bombs exploding every few days and thinking that much energy would probably affect things, well, you're right. It is affecting things. The planet is warming up, and our climate is shifting. Utah Climate Notes is a collaboration between the Utah Climate Center and Cooperative Extension, making essential climate science real for the people of Utah.